Good day. This topic is all about contagious distribution and truncated distribution. So let us know first what is this contagious distribution. If our function sub 0, function sub 1 up to function sub n is a sequence of density functions which are either all discrete density functions or all probability density functions which may or may not depend on parameters, on our p sub 0, p sub 1 up to p sub n is a sequence of parameters satisfying that our p sub I is greater than or equal to 0, and summation of p sub I, where I is equal to 0 up to infinity, is equal to 1, then the summation of p sub I times f sub I of x, where I is equal to 0 up to infinity, is a density functions which is sometimes called a contagious distribution or a mixture. Let's have an example here. If our f sub 0 of x is equal to phi sub mu sub 0 and sigma sub 0 squared of x, which is a normal with mean and a variance, and our f sub 1 of x is equal to phi sub mu sub 1 and sigma sub 1 squared of x, then our p sub 0 times phi sub mu sub 0 and sigma sub 0 squared of x plus p sub 1 times phi sub mu sub 1 and sigma sub 1 squared of x is equal to this equation, where our p sub 0 is equal to 1 minus p and our p sub 1 is equal to p, is a mixture of two normal densities. We have this whole equation here and this one, since our phi sub mu sub 0 and sigma sub 0 squared of x and this phi sub mu sub 1 and sigma sub 1 squared of x is given to be a density function. This equation here is sometimes referred to as a contaminated normal. Contagious distribution or mixtures can be useful models for experiments. Physical considerations of the random experiment at hand can sometimes persuade one to consider modeling the experiment with a mixture. The experimenter then may know that the phenomena that he is observing are a mixture. For example, the radioactive particle emissions under observation might be a mixture of the particles emission of two or several different types of radioactive materials. Then the concept of mixing can be extended. We then now let our function sub x with parameter theta be a family density functions parameterized or indexed by theta. Let the totality of values that the parameters theta can assume be denoted by big theta. If big theta is an interval, possibly infinite, and g of theta is a probability density function, which is 0 for all arguments not in big theta, then the integral of our function x with parameterized by theta times g of theta d theta is again a density function called a contagious distribution or a mixture. For example, suppose our f sub x parameterized by theta is equal to e raised to the negative theta times theta raised to x over x factorial for x is equal to 0, 1, 2, and so on, and our f sub x parameterized by theta is equal to 0 otherwise, and our g of theta is equal to lambda raised to r all over gamma r times theta raised to r minus 1 times e raised to the negative lambda times theta, with an indicator from 0 to infinity times theta, which is a gamma density, then the integral of f sub x parameterized by theta times g of theta d theta evaluated from 0 to infinity is then now equal to the integral of e raised to the negative theta times theta raised to x all over x factorial times lambda raised to r all over gamma r times theta raised to r minus 1 times e raised to the negative theta times lambda d theta evaluated from 0 to infinity. Then it is equal to lambda raised to r all over x factorial times gamma r, which we combine these two and we multiply it with the integral of theta raised to r plus x minus 1 times e raised to the negative lambda plus 1 raised to theta d theta evaluated from 0 to infinity. Then we now come up to this one, the quantity of r plus x minus 1 taken x times lambda all over lambda plus 1 raised to r times the quantity of 1 all over lambda plus 1 raised to x for x is equal to 0, 1, and so on. Then this equation, this equation here, which is the integral of e raised to the negative theta times theta raised to x all over x factorial times g of theta d theta, were evaluated from 0 up to infinity, where g of theta with indicator from 0 to infinity times theta is a probability density function. And that's all for the contagious distribution. For truncated distribution, in subsection 2.6, we indicated how truncation could be employed to generate new families of discrete density discrete densities. Truncation can also be utilized to form other families of contagious distribution. For instance, the family of beta distributions provides densities that are useful in modeling an experiment for which it is known that the values that the random variables can assume are between 0 and 1. A truncated normal or gamma distribution would also provide useful model for such an experiment. A normal distribution that is truncated at 0 on the left and at 1 on the right is defined in density form as f of x is equal to f of x parameterized by mu and sigma is equal to phi sub mu and sigma squared of x with indicator 0 up to 1 of x all over big phi sub mu and sigma squared times 1 minus big phi sub mu and sigma squared times 0. So in general, truncation truncation can be defined as if x is a random variable with density f of x and cumulative distribution big F of x, then the density of x truncated on the left at A and on the right at B is given by this equation. F of x times x with indicator from A up to B of x all over big F of x times B minus big F of x times A. And that's all for this topic. Hope you understand what is contagious distribution and truncated distribution. Enjoy your day and God bless.